Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today, we're going to review rotational motion, the dynamics of rotational motion, again about its energy and conservation of momentum. Here is a question from past AP exam. A space shuttle astronaut in a circular orbit around Earth has an assembly consisting of two small dense spheres, each of mass m, whose center are connected by a rigid rod of length L and a negligible mass. The astronaut also has a device that will launch a small lump of clay of mass m at speed v0. Express your answers in terms of m, v0, L, and fundamental constants. So here is the setup. So initially, the assembly is floating freely at rest relative to the cabin. An astronaut launches the clay lump so that it perpendicularly strikes and sticks to the midpoint of the rod as shown. Determine the total kinetic energy of the system after collision. So the total kinetic energy of the system before collision is just 1/2 mv0 squared because the two mass on the bar is at rest. What is after collision? So after the three masses actually move together, and they are not rotating because this clay hits right in the center. So we have to find the speed of after collision. To find the speed of after collision, we have to use conservation of momentum. As a matter of fact, we know in this case both linear momentum and angular momentum are conserved because there is no external force or external torque. But however, there is no rotation of masses because this clay hits right in the middle, so nothing is going to rotate in this case. So this LB equals LA tells us no information because before equals 0, after equals to 0, there's no rotation. So we need to find what is the linear momentum before and linear momentum that has to be equals to linear momentum after. From there, we can find velocity of the whole system after the collision. Then from that velocity, we can find total kinetic energy. So let's go. And v0 equals to, this is the mass before, velocity before, 3 stick together. So the total mass is 3m times v center of the mass prime. This is the speed after of the center of the mass. So v center of mass is 1/3 v0. But this is not end because they are asking us what is the total kinetic energy. Kinetic energy is 1/2 mv squared. And this m, we have 3 masses stick together, and this v is just 1/3 v0. Substitute everything in. K after is mv0 squared over 6. Question 2, determine the change in kinetic energy. Change is after minus before. This is after kinetic energy. We know before is just 1/2 m times v0 squared. So substitute everything in, you should have negative mv0 squared over 3. This negative indicate energy has decreased. Because this is inelastic collision, during inelastic collision, some of the energy changing into heat. Part 2 now, assembly. The assembly is brought to rest and clay lump removed. An experiment is repeated as shown right over here. Instead of launching in the middle, you are launching at the end. So with a clay lump striking perpendicular to the rod, but this time sticking to one of the spheres of the assembly. So determine the distance from the left end. Left end is 0. To the center of the mass of the system immediately after collision, assuming that radii of the sphere and the clay lump are so much smaller so we don't have to worry about the radius of the mass. So here to redo it, this is immediately after the clay stuck to one of the spheres. So what is the center of the mass here? So over here it says from the left. So left is 0. And here is the equation for the center of the mass. And simply substitute everything in. M times 0 plus 2m times L divided by the total mass. So the center of mass is 2/3 L. So right over here. And question number 2 is on this figure, you need to indicate the direction of the motion of the center of the mass immediately after collision. So right after collision, this center is going to move straight up because linear momentum is conserved. Linear momentum before is upward, and after, the whole thing has to move upward. Part 3, determine the speed of center of the mass immediately after collision. So again, center of the mass is not rotating, right? So only linear momentum is conserved. P before equals to P after. P before is again m times v naught. P after is 3m. The whole thing of the system moving at v center of the mass. So we did this in actually a part 1. So it's the same as 1/3 v naught. It's the same. The center of the mass is moving the same. What is different? The difference is now the mass are going to rotate. Before the mass nothing is rotating. Now the mass is going to rotate around the center of the mass. Okay, now let's see, determine the angular speed of the system immediately after the collision. So we have to find how fast it's rotating around the center of the mass. Because it's rotating, we need to use a conservation of angular momentum. So L before equals L after. L equals R times P. So before, this B means before. Before R is L over 3. P is just mv naught squared. We have to find total I, then we can find omega. What is I? I is m1 r1 squared plus m2 r2 squared. m1 is just m times r1 is 2l over 3 squared plus m2 is 2m because 2 stick together, times the distance between the center of the mass to the 2m, which is L over 3. So you have I equals to 2/3 mL squared. Now we can find, substitute everything in, R times P equals I times omega. You can solve for omega. Last part, we have to determine the change in kinetic energy as a result of this collision. So change in kinetic energy, again, is after minus before. Now pay attention. After, you have two types of kinetic energy. You have translational, that's the center is moving in straight line, and rotation, because the masses are moving around the center of the mass. And minus before, you probably say before, how do you know? Is it rotating or is it linear? Before, you just have one energy. You can use 1/2 mv squared, mv naught squared, or 1/2 I omega squared. They are the same. So you can say, consider this is rotating around the center of the mass, or you can just say it's linear. Both are the same. That's only one thing you have. So that's the energy before. So change of K. After, you'll have the center of the mass is moving linearly, plus the mass is rotating around the center of the mass, minus this B means before. So again, after mass, the total is 3m. And the center of the mass is moving at v naught over 3 squared. And here is total I, and here is the omega. The masses are rotating with this angular speed, and this is total energy before. So simply substitute the numbers, figure it out. You should have negative mv naught squared over 4 again, because collision is inelastic, so sum of kinetic energy is converted into other types of energy. Most likely it's the heat. Thanks for watching. I hope it helps. See you next time.